instead of installing air starting valve, why can't we use any other valve, like simple relief valve? That's what I was asking.
Okay. There are other means of starting the engine also. It is not that air is the only means of starting an engine. But those engines are smaller engines and they require less amount of torque to get the crankshaft rotating. In the case of a large engine, you cannot have the required speed brought up to generate a momentum which will cause further compression of the air for the next unit. So air has been found to be the most convenient means of getting the engine to start rotating itself. There is no other means to rotate it conveniently. But for smaller engines, you can have battery start. A battery start very much like what your cars and automobiles have. Even there they have diesel engines and their starting procedure is through the battery. So you have electrical starting procedure with the power initially being obtained from the battery. That is one. Then for the emergency generator, you have spring-loaded starts. It is something like, if you remember, in our olden days, we used to have small alarm clocks where we used to wind up the spring, and that spring used to preserve the potential energy. And then that potential energy was being released very gradually. A similar spring mechanism is achieved, and that can be also wound up for the emergency generator. And then you press a button, and that spring catch is released to cause a rotation of the crankshaft. Moment rotation of the crankshaft is generated, compression issues, and then fuel is injected and the engine starts. So this is a second means of starting. A third one, sometimes on the lifeboat, you do have battery start, but then you have a manual start arrangement. But manual start arrangement is possible only for a small engine. For a very large engine or for a large engine, large and very large engines, you need initial power to rotate that engine. And compressed air has been the most convenient means of starting the engine. That's all.
Yes, sir.
Okay, that's good. So let's start on our subject. And if I remember, the last part of the class that we had was regarding connecting rods. So Nu has come in now, 35. So, and this time next week, that will be 24th of November, you'll be having your class test. And I am yet to make out the question paper. I will have to make out 18 questions with 3 questions for each section. And no question will be common. Questions may be the same subject matter, but there'll be a different angle to the question. So you will have to answer what is asked of the question. Do not give information which is not been asked for. That I have noticed in some of the answer papers in your previous class test. Try to remain focused on what has been asked and answer just what has been asked. That's all. Do not give information which is related to the answer. That does not make sense and you don't get credit for it. Of course, nobody will fail. I am here not here to fail anybody. Most of the answers are satisfactory, most of them. And I would like you to put in a little more effort in the sketching part of it. An engineer's language is a sketch. If something cannot be explained, it is best to be delivered by means of a sketch. Like they say, a picture speaks 1,000 words. So similarly, a sketch drawn correctly, neatly, and it is labeled correctly, you will find the examiner, not just me, any examiner, in your favor. And if they see a somehow drawn sketch, callously made with written labels, it should be printed labels. The labels, whenever you point out to a part, keep it in block capitals. And that conveys a lot of message to the examiner. You will say this particular engineer is very systematic, orderly, and he's clean with his normal work too. Your answer script is a presentation of your personality. It is not just answering the questions correctly that matters. It is your presentation also that matters, that will derive favor of the examiner. So be a little neat, tidy, systematic, orderly. This aspect of your personality also reflects your work habits. That's the way it is. So be a little careful. You're going to be engineers, and engineers are very, very specific, very systematic, very orderly, very neat in their work. If you see the engine rooms of today, they are super neat and clean, and they expect you to be also identical to that. So that is what my point of observation is there in your answer scripts during your class tests. And this kind of test is going to also happen in your professional life. So start now in presenting yourself with an answer script which speaks about your personality. It is not just about answering the questions correctly. The way you deliver that answer, the order in which you place your statements point wise or paragraph wise with the respective heading. And one of the best ways to answer a question is start with the question itself. What is the meaning of so and so? So your answer should start. The meaning of so and so is like this. So you hit the answer, or rather, you hit the nail right on the head when you get to answer the question. That should be your approach. All right. So the last class, what we were discussing was on connecting rods, and we had finished a little bit on hydrodynamic lubrication and all that. I think yes. Let us have a look at that PowerPoint program. Yeah. Okay. Close. Oh, this is the last part of it. Yeah, we had finished all these, and I think 12 or 13. This was the last. We were talking about connecting rods. Let's have a reminder. One of the questions that is going to come to one of the sections is going to be about connecting rods. Maybe there'll be two different questions on connecting rods placed differently, asking for different aspects of the connecting rod. So let's have a run through this particular page, and we'll last finish with crankshafts. Four-stroke connecting rod, the top end bearing also referred to as small end bearing, the wrist pin bearing, gudgeon pin bearing. These are all the same, only the terminology is a little different. And in different states, in different books, different papers, you will have different terms that are used. But remember, it is the same thing. This top-end bearing has the gudgeon pin of forged steel, hardened and polished. Further to that, at the ends of the gudgeon pin, you have a groove cut out. This groove is intended to hold the circlips. Circlips are like clamps, which clamp onto the shaft and does not allow that shaft to move beyond its location. Okay, so the gudgeon pin may be fixed in the piston boss and free to rotate. That is, he's talking about the gudgeon pin. The gudgeon pin may be fixed in the piston boss or free to rotate. If you remember that diagram shown to you, a sectional view of the piston, the gudgeon pin is located centrally. And if you also have observed, half the area that the force is transmitted on is taken by the piston boss, and half the area of the gudgeon pin is taken by the connecting rod. So there are four segments over there, two on each side, which make up half the length of the gudgeon pin, which accommodates the where the diagram. No, not here. Oh, that is in the other PowerPoint. That is not here. That is in the other PowerPoint. Okay. So how do I produce that? Okay, I'll show you another diagram which has the same meaning. Okay, this is another one. So the gudgeon pin itself, when it is fitted inside the piston at room temperature, it is more or less a tight fit. But when it is working inside the engine, the gudgeon pin is reasonably free. There is no measurable clearance between the gudgeon pin and the piston boss. It is in microns. It just slips on the surface. It's working clearance. But there is a distinctive clearance between the bronze bush of the connecting rod and the gudgeon pin. And this is what I had explained to you, how lubrication of the gudgeon pin bearing can take place. It is only during the induction stroke that the oil has some ability to get between the gudgeon pin and the bronze bush for lubrication. And that lubricating oil is adequate for the next three strokes: the compression stroke, the expansion stroke, and the exhaust stroke. So that oil holds out. So that is why you have a larger clearance between the bronze bush and the gudgeon pin, and almost just working clearance between the gudgeon pin and the piston. Okay. It is centrally fixed with the help.
Can you show us the diagram, sir?
Sorry, come again. Please repeat that.
Sir, can you show us the diagram, that diagram you were talking about?
Okay, let me see if I can get it now. Okay, stay online. Fifth semester diagrams. Hmm. There's so many of them. Not here. Okay, not this one. Okay, here you are. Yeah, can you see the diagram now? Hello?
Yes,
Yes,
sir.
sir.
Okay,
We can.
okay. Now you see this is the boss part of the piston. This part where the piston is holding the gudgeon pin is called the boss. So this is one side of the boss and this is other side of the boss. It is actually, this entire assembly here is called the boss and strut region. The boss and strut region, and this is where the boss is. The boss is part of the piston which is a little thick, and it holds the gudgeon pin, this side and this side. And in the center is the location of the connecting rod. When the gas pressure acts on top of the piston, the force is transmitted through the piston walls onto the boss, and the boss ultimately transfers that force onto the gudgeon pin at the two ends. All right, the force is downwards, and the gudgeon pin, because it is forced downwards, will ultimately force the connecting rod downwards at the central portion. So when the gudgeon pin is forcing the connecting rod downwards, obviously there is no clearance between the bronze bush at the bottom and the gudgeon pin. Likewise, when the connecting rod is pushing the piston upwards, there is no clearance between the bronze bush and the gudgeon pin. The clearance only exists when the induction stroke, that means the connecting rod, pulls down the piston. When it pulls down the piston, the clearance at the top is zero and the clearance at the bottom increases. Moment the clearance at the bottom increases, the oil has a path to flow in between the bronze bush and the connecting rod. So that oil retains itself in some of the grooves which are made in the bush. So let's have a look at it now. So that oil has a chance to lubricate the bronze bush at that particular point. 1 minute. Oh, where did it go now? Sorry, that isn't this one. Uh, Yeah. So moment the connecting rod is pushing it up or the piston is pushing the connecting rod down, there is no clearance. So that is why you get lubricating oil only during the induction stroke to emerge from that oil hole which is there in the bush. Otherwise, the oil hole is kept closed during the three strokes, and only during induction stroke that oil hole is able to deliver the oil between the connecting rod and bush and the gudgeon pin. Are you able to understand? Hello?
Yes, sir.
Okay.
Yes, sir.
Okay. Let's move on. So it may be fixed, and you saw there is no clearance between the boss and the gudgeon pin. But to fit this gudgeon pin initially in the engine room, what we do is this piston is generally aluminum alloy. So we take it to a very hot region in the engine room. It may be at the close to the boiler combustion chamber, or it might be near the exhaust pipe of the main engine. So that is the place that is hottest. So the piston becomes a little hot, or rather between warm and hot. It is still touchable, but it is about 50 degrees centigrade, 50 to 55 degrees centigrade. And the gudgeon pin, we keep it in the domestic fridge. That means in the room where all our provisions are kept at 4 degrees centigrade. So once the gudgeon pin cools, there is marginal shrinkage. So the fifth engineer is told to go and bring it from there, and he brings it wrapped around in a cloth. So it retains its temperature as long as possible. So when we bring it to the engine room and we bring the piston, there is a marginal increase in the diameter of the boss opening and a reduction in the diameter of the gudgeon pin. Now, with a little oil coating, the gudgeon pin is pushed through that boss and allowed to enter in. And once it moves to a central position, we put one lock circlip over here, which locks the gudgeon pin in position. And of course, you need to position the connecting rod before putting the gudgeon pin. So the connecting rod has to be positioned. The gudgeon pin passes through the boss. The difficult part is entering the boss over here. The entry through the bush of the connecting rod is not very difficult, because there is a significant clearance compared to what you see here. So the boss, so the gudgeon pin can go through the bush very easily. And then again, because it is absolutely in line with this boss, the gudgeon pin enters this boss also very conveniently. The difficulty is getting it initially into the boss over here, because the diameters are almost equal. It is only marginally smaller because it has been cooled and the piston has been warmed up. So once it enters and normal temperature is allowed to be brought in, it grips onto the gudgeon pin. So then it is clamped here and it is no longer loose. But that is at room temperature. What happens when the engine is actually working? That time the piston is at a higher temperature, and the coefficient of expansion of aluminium is definitely much higher than coefficient of expansion of the forged steel gudgeon pin. So then this part becomes loose. Though this part is getting lubricated, some amount of oil will seep in between these two surfaces, but those are not the two surfaces which will be rubbing in. That will remain static in position. What will be rubbing, and that also with an angular motion, is the underside of the bush at this point, and marginally on the upper side of the bush when the induction stroke takes place. So only during one stroke, the upper side of the bush is taking some rubbing action. But on three occasions, on three strokes, the lower side of the bush takes all the rubbing action. So most of the oil requires to be at the bottom of the bush right here. Okay, so that is how the piston, trunk type of piston and gudgeon pin bearing works. So that is how it is. Oh, okay. That is why I said it may be fixed in the boss or free to rotate. It is free to rotate when the engine is working, but at room temperature, it is a fixed position. It is fixed centrally with the help of circlips and prevents damage and scoring of the cylinder liner. Obviously, if the gudgeon pin shifts to either side, it is going to hit the liner and it will cause some amount of damage. So here is an example of one connecting rod and a bearing. Remember, the bearing can be a little bigger than the diameter of the cylinder that you see here. So this is a possibility in some engines where they have a very large bottom end bearing. And this helps to reduce the pressure per unit area, much like your crosshead engine bearings. Now, one thing is that I have taken this diagram from the internet, and there are some mistakes in the labeling. The labeling, if you see here, number 10 is showing as connecting rod bolt. It is not a bolt, it is a stud. Remember, you cannot have a bolt and nut on the same end. Number 11 is given as connecting rod nut, which is correct. But then number 10 is wrong because it cannot be a bolt. It will be a connecting rod stud. I hope all of you know the difference between a stud and a bolt. So that is an error. I am, because it is taken, downloaded and copied and pasted from the internet, I'm not able to eliminate this word here. I think I need to be a little more computer savvy to be able to change certain data which has been copied and pasted. So this is your arrangement for a piston, a trunk type of piston where the bearing is much larger. So how do you take out this particular unit from the engine? To take out this from the engine, you will need to open out this flange by opening up these nuts, and then the piston and the connecting rod can be drawn out from the top after removing the cylinder cover. Whereas the bearing, that has to be opened out after opening this nut and this one, so that the lower half is lowered into the crankcase and taken out from the crankcase door. Likewise, if the top piece is also removed, the top half can also be removed through the crankcase door. Inside the bearing, what you have is a thin shell bearing. Now, you need a little information on the thin shell bearing. And oh, I should have made a sketch and made it much more clearer. Okay, this is section C. Okay, the beneficiaries will be section B and D, because I'll have to introduce another plate here to explain thin shell bearings. I had a little trouble explaining to section F, but they finally understood. Now I'll try the same here. Now what you see here is a thin shell bearing. A thin shell bearings are just what you see here. You see there are two sheets of metal which are curved in two halves. All right. Now these two shells actually constitute miles, or rather better than mild steel. It has got some amount of springiness in it. So it is a high grade of mild steel, and on that steel is a layer of copper. Over that layer of copper is a layer of white metal. This is the most basic. And white metal, if I've already explained to you, made of various metals. And the common metals which make up white metals is copper, lead, tin, antimony. Copper, lead, tin, antimony. It could be three of them, or it could be three of them. You may have tin or may not have tin. If you have tin, they are called tin-based white metals. And if you have lead, they are called lead-based white metal. So these are thin shell bearings, and they have no means of actually being held in place without being allowed to rotate. So connecting rod ball bearings have bearings are thin shell bearings. In fact, your two-stroke engines are also having thin shell bearings today, because thin shell bearings are easier to handle, easier to replace, lesser in cost. In all aspects, thin shell bearings are far better than white metal embedded or white metal lined bearings. So white metal lined bearings are going out of use right now because of their difficulty in replacement, difficulty in bedding, difficulty in transportation. So all these things are issues with white metal lined bearings. Thin shell bearings have become the current bearings, and I don't think you will see white metal lined bearings in your lifetime now. So bolts are a high grade steel, and connecting rod is made of cast steel in marine engines. Okay, that is about the connecting rod. A little more about the thin shell bearing. You see, there is nothing to lock the thin shell bearings in place once the keeps are fitted in place and the bolts are tightened. Once you tighten the bolts, there is every possibility of the thin shell bearing of rotating inside the keep. All right. So how is it prevented from rotating inside when it is running? And just now you saw the diagram of that piston where, oh, again it is gone. Anyway, we don't need it right now. The oil that comes from the main bearing, through the journal of the main bearing, through the crank web, through the crank pin, and out of the crank pin. there is a hole in the crank pin, if you remember that diagram right at the beginning. You see this crankshaft here. You see there are holes on the crank pin as well as the main bearing. These holes are intended to carry the lube oil. There is a hole here, there is a hole here, there is a hole here. So the oil enters through the main bearing, passes through the journal, passes through the web that you see, and comes into the crank pin. And from the crank pin, it emerges and comes through the thin shell through one more diagram, through the thin shell here and up through the connecting rod to lubricate the top end bearing, that is the gudgeon pin bearing. Now if for some reason this white metal shell turns inside the bearing keep, that means the oil passage will be blocked, because there is one single hole in the top half of the bearing shell which allows the oil to pass through and proceed through the connecting rod to go right up to the bushing on top. Now, if for some reason the shell inside, which ultimately forms the cylinder, rotates while the engine is running, that means the oil hole in the shell will shift to a new position and a blank portion will come in passage of the hole and no oil will reach the bush on top. So you will have no lubrication of the bulge bearing, and after that there will be disaster. So what prevents the shells from rotating inside? Okay, now pay attention to this. I wish I had a diagram. The shells are made in diameter a little larger than the diameter of what you see the bearing keep and the connecting rod. This is the bearing keep or the rod cap, all right? And this is the connecting rod. He has called it a rod cap. Okay, we'll call it rod cap because it caps the rod. So this diameter of the rod and cap ultimately is little smaller than the diameter of the shell, and this is in micromillimeters, all right? And when they are too tightened, there is slight amount of compression of the thin shells within their elastic limits, and it does not cause any distortion. It remains a perfectly circular body and helps to exert enormous force between the connecting rod and the top of the shell. So this enormous force on top of that cylindrical shell is what gives the required frictional resistance to rotation of the shell inside. Bigger the force, more is the frictional resistance to resist the rotation of the shells inside the keep. Get it? If the force was not there, then the shells would rotate inside very easily. So how do you exert that force? By making the shells micromillimeters larger in diameter, which will help in exerting enormous force on the shells without causing any distortion or damage, and keep the shells pressed in position and not allow them to rotate inside. Are you able to understand?
Yes, sir.
Okay. Anybody not?
Sir,
Yeah.
excuse me, sir. Sir, sir, any stress in the cell can damage it. Means it can cause an eruption. It can bend it.
No,
It
no,
can
no,
reshape
no,
it.
no.
Maybe.
Yes, yes, I can understand that worry. That is a worrisome factor. But the dimension of the thin shells is so made that it is few micromillimeters larger. So that few micromillimeter larger when it is compressed will not cause any deformation because it remains within the elastic limits of that metal. There'll be no deformation. In fact, every material has some elastic property. Even steel has got some elastic property. So that property is being utilized here to create that extra force on the shell to restrict it from rotating inside. And that is a calculated figure. So it is, you cannot really see the difference in the diameter. But if you put your finger over it, and you will feel that the ridge, that the shell is marginally higher than the level of the keep or the connecting rod. You can only feel it. It is few micromillimeters higher. It is not in the same plane. So when they are two fitted, initial contact is made between the shell and shell, and thereafter the keep and the connecting rod after tightening. When you first tighten the bolts, the first contact will be between the two shell ends. And then as you tighten further, this part of the shell will compress and this surface will make contact with that. So when you're making full tightness, it is actually the contact between the keep and the connecting rod. And this shell remains compressed without distortion or damage. Okay. So it is a calculated value of compression that comes into being. And you cannot really see it. You can only feel it as being a little higher. After fitting the shell in the keep, if you feel the surface, you will feel that this surface is a little higher. It's like that. Okay? Is it a little clearer?
Yes, sir.
Okay, let's move on. So this is your connecting rod and these bolts. Oh, another important word about connecting rod bolts. Connecting rod bolts for trunk type of engines, whether it is two-stroke or four-stroke, doesn't matter. The bolts have a limited lifespan, and that lifespan is something like 15,000 hours, 20,000 hours, or at a maximum of 22 to 25,000 hours. That's the maximum. After 20,000 hours, the manufacturer will mandatorily require you to change the bolts, no matter how good they look. You need to throw away those bolts, not use them again, and replace it with new bolts because they have reached their fatigue limit. Any further running with those bolts may rupture those bolts. It is at end position. It will break any moment. So that is why those bolts have to be changed periodically over a stipulated number of running hours. Okay, keep that in mind. And in fact, we are required to discard the bolts once we remove it, because there have been mistakes on the ships. These bolts which have been taken out because they look very good, and we being Indians as we are, we tend to preserve old stuff. So they are preserved in the storeroom somewhere, and after 5 years, some new engineer comes and says, "Oh, we have got spares, very good spares," and they try to use those bolts, and it is disaster. So you are required to throw away those bolts and not keep them. Do not store condemned items on board, because the next guy, the next engineer will possibly use it and he will have a mishap. So be very thorough in understanding this aspect of managing bottom and bearing bolts. Do not keep them on board because the next engineer will make a mistake. Okay, here the piston load is reversed during the induction stroke of the four-stroke cycle. And this allows the oil to spread over the lower surface of the gudgeon pin bearing. I have already explained that. The oil supply comes through the main bearing, crankshaft, crank pin, and up through the connecting rod. The lubricating oil which is passed through serves two purposes. One is lubrication of the rubbing parts, no doubt, and over and above that, cooling of the piston and bearing assembly. In fact, it provides cooling for any surface that it comes into contact with. So that is why lubricating oil is not only a lubricating oil, it is also a cooling medium. It is also a cooling medium. Keep that in mind. Now, how the oil comes in, I have a sketch here. The sketch I could get was a complicated one. And for me to draw a sketch, it takes a lot of time. And that time is okay. Next time I will do that. I will draw a simple sketch to make it very clear how it comes about. I think I have such a diagram somewhere. I'll have to search for it. But this is the diagram, which is one of the ways in which the lubricating oil provides lubrication and cooling. But be aware that this is not a common means of cooling the piston with lubricating oil. It is not very common with marine diesel engines. As I have seen over the years, we try to keep a simpler means. This could be an engine for a different purpose, and it could also be a marine purpose, but this is not very common. Let's have a look at it. From the outlook, you can see that this is the piston, this is the connecting rod, and this is the crankshaft. And this view is the 90-degree side view of the same piston. Now, what you see on the left-hand side top end is a pipe. It is a oil pipe or oil manifold. This pipe may be inside the engine or outside the engine. It is a common manifold. It is a common pipe with lube oil coming in from the lube oil pump under pressure. So the pressure can be anything between 4 to 5 bar because it is a trunk type of engine. When you start the engine, the pressure is 6 bar. After some time, when the oil heats up, the viscosity drops and the pressure drops to 4 to 5 bar. So that oil which is coming in into that pipe has branch pipes, lot of branch pipes, depending on the number of main bearings there are. So each branch pipe actually goes to the main bearing. So this is the pipe that goes to the main bearing, and this here is the main bearing which is supporting the crankshaft. So it enters the main bearing and it provides the hydrodynamic lubrication which I explained to you earlier in the class. And thereafter, there is a hole inside that main bearing journal, and the oil enters through that oil hole. Some of the oil, of course, escapes from the sides. And I explained to you about hydrodynamic lubrication, how the oil viscosity is the most important parameter for satisfactory lubrication. So if the oil is very thin, most of the oil will escape out from this bottom part and a little from the top part. So it has to be of the correct viscosity. It has to be thick enough and thin enough to actually lubricate this bearing. So if it is thin enough, it will go into the shaft, then travel through the crankshaft, up through the crank web, and again around the crank pin and emerge from the holes in the crank pin. It is lubricating the bottom end bearing. At the same time, some of the oil proceeds up through the thin shell bearing. You see, this is that thin shell bearing which is in position, and there is a hole in the thin shell bearing which allows the oil to pass through, go past into the connecting rod, go and lubricate the gudgeon pin bearing, and then again there is a hole in the gudgeon pin also, and the oil travels right through to the end of the gudgeon pin where it emerges from the boss of the piston. And inside the boss you have a hole which allows the oil to pass through. And inside the crown of the piston, you have a cooling coil. It is called a gallery. This cooling coil is a copper pipe which is cast in when the aluminum piston has been casted. So that copper pipe is a space inside the crown, and that space allows the lubricating oil to pass through and circulate inside the crown and then emerge from one end of the pipe back into the boss of the piston, pass out through another passage as shown on the right hand side diagram. The moment it passes out from that coil, it comes down and out from the bearing shell. This is a very unusual and reasonably rare. It doesn't make sense to have such a complicated unit. More common is to simply lubricate the gudgeon pin bearing, and sometimes you have nozzles on top where the bush is drilled with a passage through the connecting rod, and the oil comes out as a fountain on top. And this fountain of oil will cool the underside of the piston to cool the crown of the piston. Get it? That is a more common means. And as the crown of the piston is cooled from the underside, the oil falls down into the crankcase. And then the oil is splashed all over. Whatever oil is splashed through the connecting rod, through the crankshaft, is also splashed onto the internal walls of the liner. And that oil is spread on the internal walls in large amounts. To prevent excess amounts of oil going past the piston rings into the combustion chamber, you have oil control rings. Sometimes they're called oil scraper rings. And I told you earlier that if you drop oil on a steel plate and then you wipe it off, not all the oil goes away. Oil is still stuck there. This is that adhesive property of lubricating oil with steel. And that oil which remains on the surface is quite adequate to be retained and lubricate the piston rings on the surface of that liner. Remember, the liner does not have a mirror finish on the inside. It is what is called honed, Honed, honed. Honed means giving it a texture or a microscopic rough surface. Microscopic rough surface on the internal liner walls. This rough surface helps to retain the lubricating oil on the surface in spite of the scraper ring scraping of the oil. It is not a very smooth surface on the internal walls of any liner, whether it is two-stroke, whether it is four-stroke. They are purposely made microscopically rough, and that process of making it microscopically rough is called honing, Honing, honing of cylinder liners. The intention of honing liners is to help retain an oil film on the surface in spite of the oil scraper ring scraping of the oil. And remember, by hand you will find it is smooth. It will feel smooth, but it is not so smooth as you would see as the gudgeon pin surface or the piston rod surface. It is not so smooth. It is less smooth, and it is purposely made less smooth. Over a period of time, after the piston ring keeps rubbing over the surface, it does become very smooth. And then again, a rehoning process is put into action, and they have a rehoning. If you want to, actually, the subject goes on and on and on. I will not be able to complete it. But if you want to see how honing is done, go onto YouTube. You put over there honing of cylinder liners and you look at it. It is got carborundum balls. You know what are carborundum balls? Carborundum balls are the balls made of grinding stone. Grinding stones material. They are made into small, tiny balls, and they have plastic bristles for a brush. And that is lowered in the cylinder liner and twisted with electric motor. So the grinding stones, they rub against the liner walls and produce some roughness of the surface. So from mirror finish, it is actually brought to be made a little rough. And that roughness helps in retaining an oil film on the surface in spite of the scraper rings or piston rings running over them. Okay, so this is one example of a trunk type of engine lubricating oil passage. This lubricating oil not only provides hydrodynamic lubrication at the main bearing, bottom end bearing, but also provides some amount of lubrication, mixed phase, that is, not boundary, not full film fluid lubrication. It is mixed phase of lubrication at this region at the gudgeon pin. Further to lubricating the gudgeon pin, in this model, you have the oil traveling through the through the gudgeon pin up through the boss into a gallery of pipe, copper pipe, which is cast in with the piston, and thereafter it emerges from the pipe to be discharged through another drilled passage in the connecting rod and back into the crankcase. The hazard about this particular system is, if for any reason this particular unit overheats, what can happen? Then the lubricating oil will start to oxidize inside this overheated piston, because the oil has a certain limit to heat sustenance. How much heat can an oil sustain? If it is overheated, it will start oxidizing. Further to that, it will start carbonizing. And if that stage of carbonizing occurs, then there'll be a layer of carbon being deposited on the internal pipes of those copper pipes that are inside. As the layer of as the layer of carbon settles inside, then the heat dissipation capacity of that pipe is reduced. So the oil may go in reduced quantities past the pipe because there is some restriction, and thereby only have a marginal heat dissipation. Over time period, the piston is going to get hotter and hotter. And there will be a stage where the carbon completely blocks the passage and no further cooling oil goes through. And there will be no indication also, except that possibly the exhaust temperature will be higher. So if this is allowed to continue, the piston can only get hotter and hotter and hotter. And what is the outcome of a heated piston? Because it is an aluminum alloy, it cannot sustain very high temperatures. So the uh, first, uh, first condition that will happen is that the piston grooves will collapse because it becomes soft. The piston mass or the piston crown will become soft. If it becomes soft, the first liability is the grooves will collapse and they will jam the rings. Piston rings are no longer free inside. If the piston rings are no longer free inside, they cannot provide the required sealing. In fact, they will run very hard against the piston liner, thereby causing more heating and more wear down. So ultimately, as it becomes hotter and hotter, the piston will become red hot. The cylinder liner at the combustion belt will also become red hot, and the engine will start stalling. 1 minute, let me finish this. And stalling means slow stopping of the engine. And when it does stop, you will have the piston, the rings, and the cylinder liner all fused into each other. That means they are welded into each other. And no option is there except to remove the entire liner piston altogether out of the and change it. So this is what is called a piston seizure. A piston seizure means welding of the piston inside the liner. It has happened. It is not a very uncommon thing. It is reasonably common if there is neglect of engine operations. Acha, Shubham has got a question. Is there any specific oxidation reaction of oil at higher temperatures? Any oil will oxidize. Oxidize means the first stages of burning. There are two forms of oxidation. Oil which is exposed to the atmosphere will also oxidize, but it takes a lot of time for that oil to get oxidized. In fact, oxidation is a very common phenomenon in our day-to-day life. You see this white paper. After 5 years, what will be the color of the paper? It will be brown. I have some papers which are more than 5 years somewhere, and they turn brown. How do they turn brown? They turn brown with age. What is really happening is oxidation. Oxygen has an effect on this paper also. Similarly, oxidation can take place for an oil that is heated. More the heating, faster the oxidation. That is the first stage of oxidation. If the heating is more, then that oil starts carbonizing. That means the volatile constituents of the oil evaporate and the oil start becoming carbon. That means oil is basically a hydrocarbon. So the hydrogen element starts disappearing and you're left with carbon. That is what is carbonizing. So ultimately, if it is carbonizing, it is a solidifying condition. So any lubricating oil will carbonize if it is subjected to very high temperature. And now this oil is being used to cool the piston. It is being placed in a region where the temperature is quite high. So if the flow is adequate, if the speed of flow is adequate, then before it can oxidize only, the heat is removed and the oil comes out. But if the flow is less, then the time for exposure into that heat is more. So the volatile constituents will also go off. So it starts carbonizing. The means of not having this is not to overload the engine, not to have a defective fuel injector, not to have starved air supply. So all these are parameters which ensure that the engine has to run within certain temperatures and pressures. If you can maintain that, then there is no problem. And your responsibility as a marine engineer is to ensure that the engine health is always maintained during its running condition. Engine health means its temperature, its pressure, its sound, its vibration, the clearances, the cleanliness, all these are to be maintained appropriately, and then you have no problems. All right. If there any specific oxidation reaction, the question is not very clear. There is oxidation of oil if it is exposed to atmosphere. That takes a lot of time. And if it is heated, that is also oxidation. Okay. Burning of oil is also oxidation. Okay. So this is a diagram which you don't need to copy, you don't need to draw. This is only to help you understand how lubrication and, for that matter, also cooling is involved here. So lubrication and cooling both are performed in this particular arrangement. And how the oil comes about to reach the top of the piston crown is also shown to you. Okay, I hope this is reasonably clear. There'll be more of it in your sixth semester when we do the lubrication chapter. In the fifth semester, there is no lubrication chapter, so there'll be no questions on lubricating at all. Okay, so let's move on. Now we are going on to the subject of crankshafts. And after this will be combustion of fuels after this will be exhaust valves. After this, the last item in this particular chapter is exhaust valve. And in the next, this is November. Already half of November is gone. In the next half of November, next week, so you have examinations. We'll have to go much faster. Let's move fast. The crankshaft generally consists of three parts: the crank webs, the crank pin, and the main journal. A unit comprising these is called a throw of the crankshaft. All right. A throw is also referred as the distance from the center of the main journal to the center of the crank pin journal. I'll show you a diagram. The diagram helps to explain so much more. Simple sentences sometimes will confuse you, but there will be a diagram to justify these sentences. So the term throw has two meanings. One is a complete unit of two webs and a crank pin, and they are all made from one piece in some of the crankshaft. In the large crankshafts in particular, the crank throw is made up of one piece. All right. A throw is also sometimes termed as the distance between the center of the crank pin and the center of the crankshaft. Who's calling now? Oops. Yesterday in the middle, I got a call from the director. That's why I have to keep it alert. He sometimes calls for issues that suddenly related to placements, etc. So remember that term throw has two meanings. So each such unit, that means each throw, is attached to a journal to form part of a continuous shaft. You have one throw, you have another throw, you have another throw. But each throw is attached through a journal to form a complete shaft. A main bearing supports the main journal. That is the main journal that is supported. Okay, in this particular crankshaft that you see, there are 4 units or 4 crank pins. You will see one is here, 2, these 3, and this is the 4th one, 4. So these are the 4 crank pins, and there will be 4 units on that. Anyway, this diagram is not so clear. This is just to indicate to you what a crankshaft looks like. A better display would have been if we were in workshop and we could have shown you an actual crankshaft. There are so many of them in our workshop. A main bearing supports the journal. One end of the crankshaft is flange and the other end is free. You see, this end is free and this end is flange. The flange is intended to couple it to a flywheel. And I hope everybody knows what is a flywheel. And that flywheel is intended to help making the 3 other strokes in a trunk type of engine which are not imparted by the engine. The 3 strokes, energy for the 3 strokes is given from the flywheel of the engine. Only one stroke from the engine imparts power to the entire shaft, and some of the power is retained in the flywheel. So that is why the flywheel of a trunk type of engine is much larger as compared to a two-stroke engine of similar power output. In other words, if you have two engines, one is a two-stroke engine, one is a four-stroke engine, both of the same power output, the flywheel of the four-stroke engine will be much larger because it has to impart energy for three strokes, whereas the flywheel of a two-stroke engine has to impart energy for only one stroke for the compression stroke. Okay? Okay, keep that in mind. That is one important piece of information. Okay, basically there are two types of crankshaft. Some of them are one-piece construction and some of them are constructed or built-up construction. Okay, the one-piece crankshaft are smaller. Therefore, medium-speed engines and high-speed engines are one-piece, are made of cast steel or they are forgings. They can be made of cast steel. They can be made of forgings also. These are rough machined with oil passages drilled inside. You saw that crankshaft earlier and how the passages are allowing the oil to flow through. So these passages have to be drilled. Thanks. These passages have to be drilled and allow for the oil to pass through. Excuse me, just a second. These with oil passages. The fillet radii and crankpin are cold rolled to improve fatigue resistance. These are for medium speed and high speed engines. Okay. What is a fillet radii? Fillet radii is the curvature of the crankpin or the journal when it meets the web. You see, a shaft which enters a web or is part of the crankshaft is a web. If it has a very sharp ending, then there are stress concentration. And if excess load is put, it will fracture from there. So the shaft, when it meets a flat surface, is given a curvature and then it meets that shaft. Similarly, a shaft which has, say, 3 inches diameter, and then suddenly it is machined to 2 inches diameter, and it has a sharp ending. And if you give it torque, it is likely to fail at the portion where the 2-inch diameter meets with the 3-inch diameter because there is a stress concentration. However, if you have a 3-inch shaft which tapers into a 2-inch shaft, then that shaft will not fail. It is less likely to fail. So I'm giving you a comparison. You have two shafts. Both are 3 inches diameter for a certain length and 2-inch diameter for a certain length. One shaft has an immediate change in diameter and the other shaft has a gradual change in diameter. So which shaft is stronger where torque is concerned? Obviously the one with a gradual change. So wherever you have a change in section which is sudden, there will be a concentration of stress and failure may take place. So this slow reduction of diameter is actually through a radial curve, and the radius of that curve is called fillet radii. Actually, radii is the plural of radius. So fillet radii means all the fillet on this side as well as that side. That radius of curvature is called the fillet radius or just the fillet. Okay, and these are common mainly for MSC and HSC, and it is also common for two-stroke engines. In fact, all crankshafts will have fillet radii. Let's have a look at this diagram. Yeah, now here you have a crankshaft construction which is semi-built. All right. It is part of the built-up type of crankshafts. Built-up can be fully built up, semi-built up, and welded. There are three. So right now we are going to deal with the most common one, which is called semi-built up. Now this is a blown up diagram which I've made for a crankshaft. Now you see this is the web, this is the crank pin, and this is also the web. Now these three parts are actually one piece. They are made from one piece of metal. How is it made? You see, for large engines, the iron that comes out of the factory, they come out in billets, billets. They are large, circular, wrought iron, big diameter metal pieces. And these are transported by cranes. And ultimately, they go to the blacksmithy shop, huge blacksmithy shop, and they have these pneumatic hammers and furnaces. So the entire wrought iron mass is put inside the furnace. Now let us consider this as the, I need a full sheet. Just now I had, where is it? Yeah, okay, yeah. Suppose this is your wrought iron sheet that comes out from the factory. It is not so smooth, it is much rough. So it comes out from the factory. Now these are big diameter, 50, 60, 70 centimeters diameter, almost 1 meter diameter and maybe 3 meters or 4 meters length. They are huge. So they are brought in the factory. They are put in the furnace till they are made red hot, hot. And then they are put inside pneumatic hammers. Pneumatic hammers are, operated remotely. There's no person near those hammers. And they are transported all mechanically. There's no human beings. Human beings are only pressing buttons in the control room. So these are brought into those hammers, and the red hot mass is hammered at this end and hammered at this end. So they are flattened on both sides. The whole thing is red hot. And then it is bent. It is bent. After it is bent, this is flattened surface, but the central part is still round. Okay. So then, after it is bent, it is put back into the furnace and allowed to soak in. Because the moment you bend this portion, there is tensile stress on this surface and compressive stress on this side. So it is already a pre-stressed component. To relieve that stress, you need to put it back in the furnace and heat it again to the requisite temperature. So that is part of annealing. Once the stresses are relieved, then it is brought out and then the parts are machined. Once it is machined, you have this product here, what you see over here. The pin and the webs are one piece with holes are drilled to accommodate the journal. Okay, so that is one way of making semi-built crankshafts. The cast or the forged crankshafts, they come from a normal shaft. They are much smaller. So they have what are called swages, SWAGES, swages. These are used in blacksmiths' workshops. And the shaft, which is red hot, has supports at two ends and a compressing device in the middle, which offsets the shaft from its central axis at certain positions. So this offset position forms the crank pin. Then the shaft is rotated at another position, another enormous force is offsetting the crankshaft. So ultimately you have a crankshaft which has been forced with swages and very high pressure hammers or presses to have the rough shape of the crankshaft. Each pressure that is applied in a particular rotary position to give the crank angle. Thereafter, it is again put in the furnace to relieve the stresses that have been brought about out of causing that change in shape. After it is relieved, then again machining is done on that crankshaft to make your final crankshaft. If you want a detailed picture, YouTube is the best solution to ask, how are crankshafts made? You put it and you see these pictures. You're very fortunate in your generation to see things in your open eyes happening in videos. We never had this chance. The only way we learned our subject was through word of mouth and a blackboard. There was no projector, there were no laptops, there were no computers, nothing. Ultimately, when we actually got to see was in the workshops for the actual things. So we were told to actually start hammering, chipping, do most of the work with the hands. So we got a chance. But you have a chance to get a very good idea of how crankshafts are made. If you are interested, though it is not there in your syllabus to explain how crankshafts are expected. So this is how a semi-built crankshaft is made. Now here is a diagram of the shaft which is in the assembled condition. You see the main journals have been fitted in and they are interference fit. It means the diameter of the shaft is bigger than the diameter of the hole. So ultimately the shaft is fitted inside by heating the web to a stipulated temperature and get the hole diameter to increase and thereby fit the journal inside and then allow the temperatures to come down. And this is called interference fit. And the extent of interference fit is between 1 upon 550 to 1 upon 700. Next is the fillet radii. The fillet radii is based on the diameter of the crank pin. And diameter of crank pin and diameter of journal pin is almost always same. So this curvature, what you see at the end of the crank pin is what you see here, is something like this. Not all of them are like this. Some of them simply merge into the surface, but with a particular curvature. This curvature has a fixed dimension, and that is 5% of the diameter of the crank pin. So that is why it is given R is equal to 0.05 D. Diameter of the crank pin is D, and the radius of curvature of the fillet. This is called the fillet, and such radiuses all around is called the fillet radii. Okay, so that is that. So let's move on to our next plate. Okay, now fully built crankshaft has all the parts which are separately made. That means the journal is separate, the web is separate, and the crank pin is also separate. Now, that is something I find very rare. I have not come across such crankshaft, but there will definitely be if the book says so. But it is not very common. The most common is the semi-built types, which I showed you just now in this diagram. This is the most common one, and these journals are fitted in with a certain amount of interference fit. And that interference fit is 350 to 700. See, the temperature is raised to about 400 degrees centigrade. It cannot be raised beyond that. What happens if you raise it beyond that? Okay. Now, this surface which is on the journal has to be absolutely smooth, very, very smooth. Likewise, the surface on the internal surface of that machined hole has to be equally smooth. It is almost mirror finish. The idea is to get maximum surface area of contact between the two faces. If you have a rough surface, it means there are points of contact and points of no contact. It will not give an adequate grip on the item. And apart from this, the temperature is raised to only 400 degrees centigrade because above this, the metal will start to oxidize. Shubham, are you paying attention? This metal will also oxidize. So oxidation will take place and you will have a layer of iron oxide on the surface if you overheat it before fitting. So the temperature is only up to 400 degrees centigrade, which means it is hot, but not to the level where it will oxidize. If you keep it to 700, 800, it will start forming iron oxide. And that temperature and the dimension, which is differential between the journal and the hole, is between 1 upon 550 to 1 upon 700. And this is based on the diameter. So the largest diameter will possibly have 1 upon 700 and the lower diameters will have 1 upon 550. So that is the range of the interference fit. You could say, sir, why can't we have it a bigger and so that the grip will be much more? You see, after it is fitted, the web on this side is subject to hoop stress. So if you have excessive hoop stress, then this is going to rupture. the possibility of the web rupturing along this portion is a possible likelihood. So that is why the hoop stress also has to be kept within certain limitations. The grip also can be held with a certain limit. So this limit also results in sometimes slippage. You know what is slippage? That means the journal will turn inside the web. So we'll come to that much later. Let's move on a little bit. So how much time we've got? 10:42. We have about another half an hour. Okay. The crankshaft is subject to fluctuating, bending, torsional, and shear stresses, all of which produce tensile, compressive, and shear forces. You see, anything that is under stress will ultimately result in a force, or vice versa. Any force will cause a stress. Stress is force per unit area. Stress, if you take a complete area, will result in force. There, what is that called in the equation? Either side, you can follow the equation. So a crankshaft is subject to a lot of stresses, and these stresses keep changing as it keeps rotating. So it is one of the ideal items for fatigue failure. That is why the crankshaft is given an enormous factor of safety. This factor of safety lies anything between 3 and 3.5. That means even with the maximum stress, the crankshaft will not fail. The maximum stress that has been allowed, the crankshaft will not fail because it is capable of taking 3 times that stress before it can fail. Okay, so that is why it is given a huge factor of safety, and it is the backbone of the engine. If it fails, your engine fails. You can't do any repair on a crankshaft that is broken. So that is why it has to be given as complete reliability is the most important priority for a crankshaft. So the material must have high strength, long fatigue life, and form good bearing surfaces. That means the bearing surface has to be very good, because if it keeps wearing down, then the shaft diameter will reduce and there will be failure. So what is the material that is used? They are basically steel or ferrous, and carbon or low alloy steels are generally used, and the percentage of carbon varies between 0.2% and 0.4% at its maximum. So 0.2% carbon inside that steel gives the strength of the steel to a limit of 425 to 435 meganewtons per meter squared ultimate tensile stress. Okay. With increased carbon in steel, that is 0.35% to 0.4%, the strength is even more. It is 700 meganewtons per meter squared. The cost is equally more. But the engines which are using this are much higher rated engines, supercharged or turbocharged. Some of them are with second stage turbocharging. That means it is very highly turbocharged engine with enormous power for individual units. So these use crankshafts which are much stronger. And one of the highest is the one that you see here, carbon steel with 0.35 to 0.4% of carbon. For further hardening, chromium, molybdenum, and nickel is also used with the steel. So chromium molybdenum will give a surface which will have super hardness and no dent can take place very easily. And it gives a very good surface for bedding with white metal bearings. So the lubrication between the two surfaces is also improved. Okay. Now let's have a look at how you have so many different kind of forces and stresses in the crankshaft. Okay. Here is a diagram which I've copied. I could have drawn the diagram, but I think it is okay. Everybody will be able to understand. What he's trying to show you is what all forces causes the kind of stresses that you just now read about. Let's consider the force coming from the connecting rod in this angle as this arrowhead shows. You see, this is the length of the crank pin, and the force may be considered to be acting at the center of the crank pin. So that crank pin is subject to force from the middle, so the crank pin is going to bend. If it bends, it means the opposite side of the crank pin is under tensile stress, and the upper side of the connect of the crank pin is under compressive stress. So this continuously keeps changing. Moment it goes to BDC and comes up from the other side, it is the opposite on the other side. You see, on the other side, it is being pushed upwards. All right. If it is being pushed upward, that means the bottom side, which was earlier the compressive side, this side, is going to be under tension. So as it keeps rotating around the whole circle, the stresses keep changing on the surface of the crank pin. All right. That is only the crank pin. Now let's look at the crank web. The crank web is being forced downward by means of this crank pin. So obviously this crank web is going to bend because it is supported at the other end by the journal. So moment it is forced this way, it is bending to cause a tensile stress on the upper surface and a compressive force on the lower surface. Okay, so the whole crank web is being bent because of that force. Other than this, you see, the crank pin has got a force this way which is causing it to bend, and it will cause the entire crank web to twist. It is getting twisted about the central axis, which is from the crankshaft to the crank pin. About this is, it has got a twisting of the crank web. So ultimately, the crank web is under a shear stress. The shear stress. So that is brought about by twisting of the shaft, a little bit of a torque that is given. Okay. Apart from this, let's take a look at the journal. The journal is getting a rotary force or a torque or twisting moment, which is giving a shear stress on the shaft also. And this is continuously changing. When the crankshaft is in the other direction, the forces are all reversed. So it is under continuously fluctuating. That means at one point it is more, at one point it's less. At one point it is compressive, at one point it is tensile, at one point it is torsional. So all these forces are continuously changing within the crankshaft, giving you various types of forces. And that is why the crankshaft is subject to fitting failure. This is a very important aspect of understanding how the crankshaft is under a lot of stresses, and these stresses are not just static stresses. They are keeping on varying in their mode as well as in their level. A mode means compressive or tensile, and level means more or less, because the gas pressures are also varying, so the forces are also varying within in their levels. Okay. Next, what we have. For fully and semi-built crankshaft, assemblies are made in the vertical position to avoid distortion. Just now you saw this diagram where it showed, what is that diagram? Oh, miss, we missed out something. Oh, we were missed out. Yeah, if after this, we were supposed to come to this diagram. Yeah, so this one was the one which we are showing you. Fully built crank. Actually, I tend to go a little off the topic or beyond the topic. So fully built crankshaft has all the parts separately made and assembled, that you have understood. Semi-built one is the one I explained to you. And this particular crankshaft has got a hole drilled through the crank pin to reduce the mass. If you reduce the mass of the crank pin, then the centrifugal force which arises in rotation of the crankshaft because of the offset mass of the crank pin is also reduced. Ultimately, the bearings on the main journal is also reduced if you are able to reduce the mass of the crank pin. That is it. That is why you have hollow crank pins. And in some cases, you will also have hollow journals. But hollow journals don't make so much of a sense because they are not having any centrifugal force involved. The crank pins have a lot of centrifugal force involved in them. So fully built crankshaft, semi-built has the crank pin and with units as shrunk on. So this is where the shrunk fitting or shrink fitting is done on the crank web. Next, you see, when I explained to you that the whole crankshaft, the crank throw is bent and made. You see, the material has got a grain structure. Grain structure is a very important feature where the stress concentration is involved. So if you can maintain the grain structure uniformly, then the strength of the crankshaft is much more. So you see here what he says, cold rolled radii. Cold rolling is using rolling pins which press with enormous force, pressure on the surface to make it harder. Make it harder. Moment you press steel with another surface, it makes that surface much harder. And it is done in the cold condition. And when that surface is pressed, that surface end has got a curvature. It is like having a wheel, a roller on this surface rolled over with the curvature. And the curvature of the wheel end is the radius, fillet radii. So when it rolls over, this surface of the curvature is also hardened to its maximum. This is what is cold rolling. In the cold rolling, you have these cold rolling pins. They are made of extra hard material and they can exert enormous pressure. And the crankshaft is rolled through these pins to give a very hardened surface. Okay. And the hole is bored through the crankpin, reduces weight. Okay, this is one type of crankshaft. You need to have a hole drilled also to allow the oil passage to come through. So this crankshaft does not show the oil passage here. So it may have a different form of lubrication or different type of passage of lubricating oil. The crankpin, two webs produced as a single forging, note grain continuous grain flow. So that is why, because it is a one-piece forging, it has got a grain flow that is uniform, which helps in giving strength to the material. Whereas where the journal is fitted, you have a slightly increased diameter at the portion where it is shrunk fit, because the web is subject to hoop stress. Likewise, there is hoop stress, hoop compressive stress on the surface at which it is gripped. All right. And this place which is gripped and under hoop stress is only a thin layer. And that thin layer is the difference in the diameters of the portion that holds the bearing and the portion which is actually shrunk fit. So the hoop stress is not extended to the portion which is supporting the bearing. That is the whole idea. So he says increased diameter of the shrink fit prevents hoop stress extending to the bearing surface. So the hoop stress is only in this particular part, which is in the raised diameter in line with the bearing portion of the journal. Okay. This I explained to you, that further hardening chromium and molybdenum is used. Then you have the diagram which shows you all the forces and the stresses thereof that emerges from a crankshaft while it is working. Next we have, for fully and semi-built crankshaft assemblies are made in the vertical position to avoid distortion. Just now I showed you the diagram where the journal is fitted in the horizontal. In practice, when they are assembled in the manufacturer's workshop, the web is kept vertical in a way where the journal has to be lowered under gravity gradually and then allowed to be fitted in. They may use a little pressure to push it in, because the moment it makes contact, the temperature starts changing. So it is brought there and little pressure is put, but it is ideally fitted in the vertical condition so that there is straight gravity force bringing it down into it. In the horizontal position, there are 360 degrees of possible distortion taking place. Webs are heated to 400 degrees centigrade and journals are inserted with an interference fit of 1550 to 700 of shaft diameter. Okay. This I explained to you why. The crankshafts are sometimes made hollow to reduce weight and out of balance effects. Out of balance effects means the centrifugal forces that are being thrown around with the crank pin offset from the central axis of the crankshaft is also reduced if you make that mass of that crank pin lesser. And that mass can be lessened by having a hollow crank pin. Semi-built crankshafts are a better option with better grain flow structure. That is the diagram I showed you with the grain flow of the material. Okay, last one is a very important point. Reference marks are made on journal and web to check the slip. You see, the journal and the web is shrunk fit. It is not locked with or welded. It is shrunk fit. There is a possibility of it slipping inside, but calculated shrinkage is intended not to cause slippage under normal loads with a level of factor of safety, with a margin of safety. Okay. But if you exert it to a force beyond that margin, obviously there will be slip. That means there will be slippage. And which one will slip? Which unit of a crankshaft will slip? That is for you to think and decide and tell me. Okay, let's have a look at it. Now, this slippage, how do you find out that the crankshaft has had a slippage? The slippage is observed on the inside surface of the web. And this is the diagram which will show you how it is mentioned. Now you see this crank pin has been cut off. It is a section diagram. So one half of the throw is what you're observing. In other words, you're inside the throw and you're observing one side of the web. Now the crank pin has been cut off, so one part of the throw is removed. And on this surface of the web, you will be able to see the journal which has been shrunk fit inside the web. And there are two punch marks which are made in line with the center line of the journal at the very points where the two surfaces are making contact. Okay. If there is slippage, then there'll be a change in the positions of the two punch marks and they will no longer be in line. Just as what you see here, where he has made a mark right on the edge and this has shifted and there is indication of slippage. A better indication would have been if two separate marks, punch marks are made close to each other. And that is what we see on board the ships, that there are two punch marks very close to each other, but in line with the center line of the crankshaft. Okay. Now, slippage. What crankshaft slippage occurs between web and journal? So this is your web and this is the journal. So what is the cause of slippage? Suppose you overload the engine, there is a possibility of slippage. That means the amount of torque you're trying to transmit is much more. You go beyond the 10% limit that has been given. You could have slippage. Next is hydraulic lock in the cylinder. If there is water or oil inside the cylinder and you try to rotate the engine with air or turning gear and that, or it even fires, you start the engine with oil or water inside the cylinder, one of the units, then that liquid is incompressible. So the reaction is the force again on the connecting rod and on the crank pin and on the web against the journal. And then you have a slip of the crankshaft. Other than that, if your propeller outside the ship is hit by a ice or a floating mass of ice, or if it hits something solid, the propeller, remember, is not so soft. It is very, very strong and it is not going to fail. It is going to cause a reaction to the entire propeller shaft and cause it to bend, cause the slippage to occur. And any extraordinary force on the shaft will cause slippage. And here is the actual photograph. Just a minute. I'm taking a 5-minute break. The person has come to clean the room. I will be back at you. Have a look at this diagram and observe how slippage takes place. Okay, guys, sorry for that interruption, right and left. So I was talking about slippage of the crankshaft. Here, what he has done, he has made a central mark right on the joint between the journal and the web. The scale is given only to give you a visual idea of how size of that mark is. So the real punch mark is this, what small little mark that you see, and you will see another mark which is on this part. I think it is there, but he's not kept it. And these two are in line. In this case, the marks have not shifted. So part, he made a semicircle on the journal and a semicircle on the web. But in this case, it is indicative of having shifted. So there has been a slippage over here, and the cause could be anything with an extraordinary force on the shaft. That is what it is. Okay. Next point we have is the last page. Oh, okay. We give it at this point up till today. I don't have, I'll have to finish off a little bit, and then we'll include the exhaust valve possibly in our next class that we have. And then we shift to a complete new chapter, which will be on combustion and fuels. The next chapter is combustion of fuels in ICE engines. We will start with the various types of fuels that are there, combustion processes, but you will also have to keep yourself well aware of the modern trends that are taking place. There has been a lot of webinars and seminars on how to stop carbon discharge in today's atmosphere. So carbon-free fuels are much in question. Oh my God. Okay, good question, Shashwat. Why don't we provide keyways so that there is no slippage at all? Oh, this is a very, very loaded statement you're making. Very, very loaded. How much time do we have? Okay, we have 2 minutes. You see, Shashwat, I answer that, see, keyways will cause additional stress generating points and the chances of failure will be much more. That is why keys and keyways are locations where your failure will emerge without fail. It's become like that. That's why you have propellers which are fitted to the shaft without any keyways. It is just the frictional force between the boss and the propeller which turns the propeller. There are no keys and keyways. Keys and keyways were when my granddad time when they were using keys and keyways to fix shafts. Now keys and keyways are totally out of question. They are stress generating points and most likely areas of failure. But I have a very important question for you, which you need to do thinking. You have seen that the crank pin and the web is made one piece. Okay? Why couldn't the journal and the webs be made one piece and the crank pins be shrunk fit? And because the torque is being transmitted, there will never be any slip. Isn't that Shashwat? If you make the journal and the web of one piece and the crank pin is the one that is shrunk fit, why wouldn't that be a better solution? Think of it and give me a justified answer why the crank pin and the webs are one piece and the journal is shrunk fit, giving a possibility of slippage. Have you understood my question? Why is it that the journal is shrunk fit and not the crank pin? Okay, Shashwat, rack your brains, and next class we will see if you can give a very, very well reasoned answer. These are what make you an engineer. You must understand certain issues, why it is made that way, why not the other way. Okay, till then, bye bye and take rest. I'm going to have a cup of hot tea. My throat is in a bad state. Today is Tuesday. I don't have immediate class, so it will be till tomorrow. So be ready for next week. The class test will be starting exactly 9:30. We finish at 10:30. By 10:45, you're supposed to upload the answer scripts. I will, in this class only, you can upload it in the, I think we'll follow the same procedure like last time. Okay. So if you have any questions and if you have any questions, you can